So we've seen from the course on the calculus of variations that nature tends to minimise a particular quantity. Now the quantity it minimises in this case is called the Lagrangian, and it's given by the difference between the kinetic energy T and the potential energy U. So the Lagrangian is equal to T minus U. So if we can find out what this Lagrangian term is, then we can use the Euler-Lagrange equation in order to solve for a set of equations. So let's go ahead and we'll find out the kinetic energy, and then we'll find out the potential energy of the double pendulum, and then we'll work out what the Lagrangian is. So let's get to that now. So let's start off with the kinetic energy T. Now we know that the kinetic energy is given by a half mv squared. But the velocity here, we've seen that we've split this into the two components. There's an x component of the velocity and a y component of the velocity. So we've already worked out x1 dot and y1 dot. So we have to square those together, and we have to multiply them by a half m1. Now we have to do the same for the other mass, for the second pendulum. So the second pendulum, the velocity is going to be given by our x2 dot and our y2 dot, which we've already found out. And again we'll have to square these and multiply them by a half of m2. So this is the equation that we want to use. So if we take our four velocity equations that we've seen in the last slide and we just substitute them into this equation here, then we can see that we're going to have, for our x1 dot squared, we'll have L1 squared theta 1 dot squared cos squared theta 1. For our y1 dot squared, we're going to have L1 squared theta 1 dot squared sine squared theta 1. So I've just put the velocity equations into this equation and I've squared each of them. So check the velocity equations there and ensure that you agree with these values that I have. Now the second term is a bit more involved. We've got our half m2, and we've got x2 dot squared plus y2 dot squared. But x2 dot is going to be given by this value L1 theta 1 dot cos theta 1 plus L2 theta 2 dot cos theta 2, and this is all squared. And the second term here, y2 dot squared, is going to be L1 theta 1 dot sine theta 1 plus L2 theta 2 dot sine theta 2, all squared. So now we have to multiply out these squares, so we'll do that next. So we can leave the first term as it is, so this term here is just the same as this term here, we've not done anything to it. Now the second term here, we're going to multiply out the squares. So whenever we multiply this term out, we're going to end up with three terms. We'll end up with this one squared and this one squared, and twice the value of this one times that one. And the same for this here. So we'll end up with another three terms for this and three terms for that. So let's go ahead and we'll just do that now. So we're going to have a half m2, and we're going to have our L1 squared theta 1 dot squared cos squared theta 1, the first term, and then when you multiply the two together and add, you're going to have 2 L1 theta 1 dot cos theta 1 and L2 theta 2 dot cos theta 2, and finally we square out the last one. Square those out, we get L2 squared theta 2 squared dot and cos squared theta 2. Now we do the same for the last term here, so we're going to end up with three terms. We're going to have the square term here, which is the L1 squared theta 1 dot squared sine squared theta 1. We're going to have 2 times the multiple, so we're going to have 2 L1 theta 1 dot sine theta 1, L2 theta 2 dot sine theta 2, and finally we're going to have the square of the last term, which is going to be L2 squared theta 2 squared dot sine squared theta 2. So we've just multiplied those out. So I suggest that you sit down with a pen and a bit of paper and just write these out yourself to convince yourself that everything is in fact correct. So now we can jump from this line here to this line here. So let's go through each of the terms and we'll see how we go from this line to this line. So I'll change the colours here, and let's say we look at the first one is easy enough. If we take this one here and we're adding on this one here, well, we know whenever we add sine squared theta plus cos squared theta is just a value of 1. So what's going to be left over is just our L1 squared theta 1 dot squared times the half m1, and that's this term here. So we've got our half m1 and we've got our L1 squared theta 1 dot squared. Okay, so that's this part of the equation here. Now let's look and we'll see if we can find out some other simplifications. So in here we've got our L1 squared theta 1 dot squared cos squared theta 1. So I'll put a colour around this. Now further down in here we're going to have an L1 squared theta 1 squared, so let's see if we can find it. So here it is here, we've got L1 squared theta 1 squared dot, and that's sine squared theta 1. So if we were to take this one and this one, then you can see the cos squared plus sine squared is just a value of 1. So we're just left with a half m2 L1 squared theta 1 dot squared, and that's this term here. So we've got our half m2, so this is our half m2, and we've got our L1 squared theta 1 dot squared. Okay, so these four terms here are given in this first term here. So now if we take this term here and this term here, so I'll put these in different colour. So we're looking at this term and we're adding on this term here. So we can see that both of these are multiplied by the half m2, and the sine squared theta 2 plus the cos squared theta 2 is just a value of 1. So you're just going to be left with our L2 squared theta 2 dot squared sine squared theta 2, and that's this term here multiplied by the half m2. So this is the blue term. Now finally what you're left with are these two terms here, and this is when you use a little trig identity. So the trig identity you're going to use is cos theta 1 minus theta 2 is equal to cos theta 1 cos theta 2 plus sin theta 1 sin theta 2. So that's just a double angle formula for a trig identity. So we can see here that we're going to have the 2 is going to cancel with the halves. Okay, so it's a half times this 2 and this 2, so those will cancel out. And we're going to multiply the two together, so we're going to have our value of m2 times the L1 L2 theta 1 dot theta 2 dot, and we take out this factor here of the cos theta 1 cos theta 2 and the sin theta 1 sin theta 2, and those go into this identity cos theta 1 minus theta 2. So we're left with this equation here, and this equation is the equation of the kinetic energy of a double pendulum. So take your time and write this out yourself and convince yourself of it and see exactly how it's working. Now we'll move on and we'll look at the kinetic, the potential energy of a hanging rope of the double pendulum in the next video. Goodbye.